All right, so my name is Kellen Green. I'm a senior software engineer here at Splunk for the past 5 years. Now, I've worn quite a few hats during my tenure here at Splunk. I was hired as a PHP developer. Splunk no longer writes PHP. I've been an AWS Cloud Ops engineer. I've been the guy who orders beer. I've done a lot of things. Today, I primarily focus on web technologies like JavaScript, CSS, HTML, and REST architecture, as well as dabble in other higher level languages like Node and Python. Now, throughout the years, I've developed a pretty strong understanding of the web database, or of the database architecture landscape as it currently sits. Products like MongoDB and the various incarnations of SQL, while they're very complex, I can for the most part wrap my head around how they function. After joining Splunk, however, it became very clear that this was something else quite different. Suddenly gone were the field types, storage schemas, and index definitions. Initially, I just chalked this up as Splunk is magic, and like many, I assume, slowly began to take the system for granted. That was until our new marketing campaign came out. It's not magic, it's Splunk. Now, throughout the years, naturally, I've learned that why people think it's magic and what is actually under the hood. But to many, I'd imagine this is true. Splunk is magic. The things it does is phenomenal. So today, I thought it'd be a great opportunity to shed some light on some of those magic bits that go into making up a search on Splunk. So in doing so, I want to teach 3 core concepts today. 1, I want us to develop a deeper understanding of the components that go into us making up a Splunk search. 2, I want to increase the performance of your searches using more efficient queries. And then lastly, I want to obtain a stronger grasp of which development types are better suited to which specific deployment types. So whether it's a search head cluster or a distributed search. Now, the data set for today's data is going to be a small 26-event CSV file. I know for Splunk that is comically small, but to help visualize, it's a good size. So we're going to have 1 event per day from September 1st through the 26th. Each event is going to occur at a random hour. It will contain 2 fields, foo, which are going to index in our indexes.conf file, and it's going to ascend from A to Z, or descend rather, from A to Z through time. Our second field is going to be an unindexed field called bar. It's going to ascend from Z to A through time. And then lastly, this is all going to be thrown in the conf 2017 index. All right, search number 1. Index equals conf 2017, foo equals 0. We're going to run this search from September 1st through the 27th. Now, you might be thinking, if foo is A to Z, and we're going to search for foo equals 0, that's just going to return nothing, right? And you'd be right. It's not. But actually, quite a lot goes into something as mundane as a no results found search. So let's take a look. So the first thing that's going to happen is the user is going to come up with a query. It's going to get sent to the search head. That search head will then copy it with the number of indexers it has, and then send that off for further processing. It's this stage in the pipeline that I want to focus on right at the moment. So let's head into the indexer. So the indexer has received the search. It's going to go into its indexes directory, and it's going to start the process. So in Splunk index, under var lib Splunk, we arrive at the indexes directory. This is the root directory where all your indexes on that index are stored. So the first thing we're going to do, we're going to check if the index that we queried has a directory that exists. So in our case, we searched Splunk conf 2017, and we can see that that directory does indeed exist. Now, when you do a index star or any other of the wildcard searches on an index, you're going to force Splunk to do the same thing across all indexes, and that really impedes performance. It all runs separately, but at the same time, you're just doing more processing than really needs to be done. So in general, specify the right index, and it'll help you. Moving into the Conf 2017 folder, you can take a look. There are going to be two types of files we want to pay attention to today. Our first is the cold DB directory. This is going to house our older data that we still want searchable. So this is great if you want to implement cheaper magnetic disks for your older data that you still want to be able to look at, but also it doesn't need to stay on expensive SSDs. The second one is the DB directory. This is going to be for our fresh data that is still in high demand. And then lastly, the indexes.conf file, we can specify when we want our new data to roll into a colder, older storage. So that's all configurable. Our data's from today, so we're going to move into the DB folder. So this is where all of our buckets live. So Splunk splits all of its data up by time range. So keeping with my theme, there are two folders we're going to take a look at. Hot, which is all your data that is still being written, so data that's coming in, that's going from memory to disk, this is where it's going to live. And then warm buckets, which are event immutable, so no more data is being written. They can be modified, but nothing is being added. So, and these are split up by the time range of events that are contained within inside of it. So you can see we have two here. We're searching from September 1st through the 27th, so we know to pick the bottom one. And then lastly, much like specifying an index, specifying a strict time range, it's just making Splunk do much less work than it needs to. So if we had not specified a time range, we'd have to go through the hot bucket and then both warm buckets, in addition to the cold if it had existed. All right, moving into our bucket. Take a look inside. Got a lot of files here. Now, scanning an entire bucket to see if an index is inside of it is really expensive in both CPU and disk I/O. So what we need is a quick and more efficient and more important space-efficient way to determine is foo equals 0 even in this index. This is where the Bloom filter comes in. So the Bloom filter, it'll tell us if with 100% certainty whether a term is inside of our index. So what we do, we have a long array of ones and zeros. The size of this is dependent on how big your bucket is, which is all configurable. What we do is we hash that term several times along the length modulo of the array. So in our case, we hashed it twice, and we have a 0 and a 7. What we then need to check for is if each point contains a 1 value. If it does, then we are likely to contain that event. Not 100%, mind you. In order to save space, typically about 0.1% of the time, you'll get a false positive, but never a false negative. So in our case, we check the 0 index, which points to a 1. Great. We're free to continue. Then the second one, it points to a 0. So at this point, Splunk can go, okay, 100%, this term is not in here. I can end the search and just say no results found, which is what we'll do here. So, for search terms that are common, this is actually no performance benefit whatsoever. If anything, it's actually a couple milliseconds performance hit. But for searches that are uncommon, so either they are rare or they don't exist at all, this is a massive performance increase. We're talking up to 100x. So on the range of scanning the index, which takes about 1 to 2 seconds, versus 10 milliseconds. So in general, this is something that just do it. Just take the 10% or the 10 millisecond hit. This was added in Splunk 5, so it's nothing you need to worry about anymore. But before, this is what happened. All right. Moving on to our next search. So foo equals A and bar equals Z. Now, if we remember, foo is indexed and bar is not. But as we'll see, these actually give the same result, remember, because A is descending and bar is ascending. So we get that same result from September 1st. Now, as we'll see, since one is indexed and the other isn't, these will take vastly different approaches to come to the same result. So staying in the same bucket from earlier, _1, take a look inside, same files. After we've determined that the Bloom filter said, yes, events are most likely within this bucket, we then arrive at the TSIDX file. So this is the primary way that Splunk will reduce all the results inside of your bucket. So it's lexigraphically sorted, so roughly A to Z, of all the terms that are inside of the bucket. And then, side note, the pipe delete flag to hide events is also set within the TSIDX file. Now, before we search through TSIDX, we actually need what's called a Lispy query. So this is given to us by the search head at search time, and it is what the indexer will use to search through the TSIDX file. So in our foo example, foo A simply becomes foo : in Lispy, which roughly translates to, give me all the events where foo equals exactly A. Now, Lispy for unindexed fields works a little different. Does anyone have a guess what bar Z would be in Lispy? Any brave souls? It is Z, very good. So bar in Z is Lispy, or bar Z becomes Z in Lispy. So this roughly translates to, all right, I need all events inside the TSIDX file that contain Z anywhere. Now to me, when I first learned about this seemed very odd. Why would I want more results than I know are in the TSIDX file? But as we'll see in a little bit, there's actually a good reason for this. So after we've given our TSIDX file, our Lispy query, we come back with results in memory. So when we do foo : A, we'll get the one result back that we wanted. Great, that makes sense. For Z, we get two results. We get the one that we wanted, which is the AZ event, but then we also get an extra one with ZA, because foo equaled A, or foo equaled Z, so therefore it returned it. You can actually see this happening within the job inspector. So on our bar search, bar Z, you can see that the number of scanned events was 2, but it only returned one result. And then vice versa, with the foo A example, we see one scanned event, one returned result. I'll also note that search.log, if you click on this link and then Control F for Lispy, you can actually see the query of the search that you're running at the moment. So that can be handy sometimes. All right, so we got our big arrays of all our data. Well, big 2 in this example, but let's pretend it's huge. So we have our big array of TSIDX results. We now need to retrieve them from disk. So we're going to move into the raw data folder. So this is where your actual events live on disk. So in keeping with the theme, 2 files we need to pay attention to. We have journal.gz. So this is compressed slices of raw event data and metadata. Then the second is slices.dat. So what slices.dat is, it's going to be a map between the events that came out of your TSIDX file and the slices that are in your journal. So we need to map the two together somehow. So this is where that happens. And then lastly, the extra events that don't match our query, this is where they'll be extracted during the search process. So the same events will be sent back to the search head, but it's this step where they will be filtered out for additional parameters. All right, so the cons of unindexed field. Obviously, we increase the potential matching results coming out of TSIDX. This has 2 potential consequences. One, we're going to increase the memory consumption of our system with an increased array size, given the events that came back. But most importantly, we're going to need to decompress all those events. So this will lead to more CPU cycles being used on events that we don't necessarily want in the first place. So my natural conclusion with this was, why don't we index all the fields? Seems like we should do that. There's one giant gotcha with this. So indexing everything will quickly explode the size of your TSIDX file. This leads to bad performances across the board. So it's not something we typically recommend. However, there is a certain instances where indexing a file is actually beneficial. And bear with me on this mouthful. We only recommend indexing for fields whose key val pair is important and has a value which frequently occurs in other fields. So clear, right? Everyone's got it? Great. Let's go through an example of that. If foo and a together are important and often searched, but bar a, baz a, biz a are also common occurrences, then that might be a time to say, all right, let's index foo because it's just returning way too many results and we're having to filter it out. So there are certain instances where this can be beneficial. So a good way to determine whether you might have a field that meets this criteria is with the walklex command. So what the walklex command is, it gives us a way to shove a Lispy query into a TSIDX file and get the number of results back, and tell us how many results it found inside that TSIDX file. So if we take our foo : example, we can see that, yes, it returned the one result that we expected. And then likewise for z, we get the 2. So if you have a search that's returning hundreds of results and you know there's only like 10 or 20 that you actually want, might be something to consider indexing that field for future searches. Okay. Example 3, star A and A star. Again, you know the drill, same results. And actually this time, even the job inspector doesn't give us much hints as to what's happening. But one is better, I promise. We'll find out here real shortly. So for a trailing wildcard, which is A star. So if we remember, the TSIDX file is sorted alphabetically or lexicographically. We're going to do a binary search into the first result that matches our query, which in our case is foo : A. Then we're going to work downward until we come to a result that does not match our query. So in our case, we move down to foo B and go, oh, that doesn't match A star. So we're good to stop at that point and just return that single event. For leading wildcard, the same thing happens at the beginning. Binary search, found foo A. It matches, great. However, this time, we don't have the luxury since the field and the value, the asterisk comes in the middle. So we don't have the luxury to just stop at the next one. We have to go all the way until the field actually doesn't match. In this case, it's 24 events, no big deal. But if you had, say it was a ID and then a unique ID identifier, it could be thousands. So in our case, we hit G and then we go, all right, we're good to stop. So performance degradation on the same event, but you always want to go for the trailing. Now a trailing wildcard on unindexed. Any other Lispy guesses for bar star Z? It will search the whole index. Very good. Very good. So Lispy for this query is actually just an empty string, or brackets rather, which means we're not even going to touch the index. We're just going to say, hey, I need everything, and all the processing is going to be handled within the journal. So even if you needed one result, you're going to decompress every event in that bucket and then return it, and then return what matches to you. So in general, always try to do a trailing wildcard. All right, transactions. So we're going to do a stat versus a transaction example. Now, say we wanted the number of events that occurred per hour in our event set. Remember the hour was random at the time of creation. And once transformed into a chart, both get the same result. But let's take a look at why these two searches take very different routes to come to the same conclusion, as we've seen before. So we've spent most of our time on the indexer at this point. Let's move back up to the search head. So at this point, our indexers have the search in hand. They're going to grab the raw events for us. They're going to send those events back to the search head, and this is where we'll continue our journey. So we arrive at what's called the dispatch folder. It's under search head, var run Splunk dispatch. So this is a directory of all the active searches being ran on that search head. Your SID, your search ID, can be found in the job inspector. Let's go ahead and pretend we're 146. Moving into that folder, we call it the search folder. This is a collection of all the events that are being returned from the indexers. So if there's multiple indexers, it's going to be thrown all the stuff back at this folder. If you watch this folder on a live search, you'll see stuff being written, deleted, overwritten, touched, all sorts of stuff. For today, again, 2 files that we want to take note of here. The results.csv.gz is our actual compressed events that we'll see in the UI. Along with timeline.csv, which is going to be the UI timeline bar in the UI, which, as we see, this is where your results live, and then this is where the timeline gets generated. Now, you might be thinking, what did all that have to do with transactions? So, going back to our workflow, we have our searches getting transformed into logs, being sent back to the search head. But this is the point where all the transaction processing happens. So it's going to take all the logs and it's going to send them all back to a single search head before being turned into our pretty graph and being sent back to the customer. So this is a little different than what's going to happen on the stats workflow. So we're going to have, again, same searches as before, being turned into logs. But this time, stats can run on all the indexers, and it's free to do them across all indexes. It will then turn those events into analytics, which gets sent back to the search head. So those analytics, instead of having to send all the raw events back, it can just send the little bits that it needs to fulfill the search, which then gets sent back to the user. So what this means is things like search head clustering will actually only increase the performance of your transactions if you're running multiple in parallel. So if we're running one search head, only that first search head can do any work. The other 2 can't help. We'd actually need to be running 3 to be able to take the full benefit of all of our search heads. This is different than a distributed search or an index cluster, running a stats command or an eval. So in this instance, we're able to spread our load across all 3 before being sent back to the search head. There's one last thing that's different. So stats inherently only concerns itself with one event at a time. This means it only requires one pass to do the computation we need to complete our statistic. So for example, for stats count, like on a stats count command, Splunk just needs to return the value plus the number of occurrences that pair contained. So for example, hour 9 had 2 events. That's all the search head needs to know to be able to complete the statistic. Transactions, on the other hand, another mouthful, but Splunk must iterate over each event for every transaction window, which looks like something like this. So for every event, we have to run through all the events to make sure that no other event match that transaction window, and then mark the start and stop times, plus the duration and the events. So this gets you a time complexity difference between stats of n and transactions is n squared. Plus, it's all running on the search head. So you can see where performance quickly degrades when using transactions in this manner. Okay, so transactions run on the search head, and stats run on the indexer. So what if we pipe stats into a transaction? Where does that run? Is it the indexer, the search head, the browser? JavaScript's getting pretty fast nowadays. You never know. We have some WebAssembly in the background. So the rule is Splunk will inherently run everything it can on the indexer until it hits a slow command, which forces it to do otherwise. At that point, we then have to say, all right, got to send everything back. I can't do the search on my own. So what does that look like for the search? So we enter with conf 2017. The indexer goes, oh, I can do that. That's fine. Oh, we're going to do a transaction. I can't do that on my own. I have to stop here. So at that point, everything following that part of the transaction has to be sent back to the search head. Even though it's a stat command, it can't do it on its own. It needs the rest of the data to be able to fulfill that query. So joins would also be another example of a command that would do something like this, that Splunk goes, can't do it, got to send it back. One way to tell if one of your searches is doing this is in the job inspector under remote search. So this is the query that your actual index is running to determine what's going to be filtered. You'll see things like pre-stats and pre-transaction, and then you'll be able to tell, oh, like in this example, stats didn't show up, so it's being done up at the chain. All right. So quick takeaways. Stats and eval, you've heard it 1,000 times in all the documentation, but hopefully you have a little more context as to why they are superior to transactions. And then trailing wildcards, always better. If you need that functionality, try to get away with using those instead of a leading wildcard. And then look into indexing important fields whose values are shared with other fields, like the foo a example from earlier. And then lastly, move the slow commands as far right into your searches as you can. So if you could have done that stats before the transaction, then you can go, okay, the search head or the indexer can at least say, all right, I can do this part, and then let the search head do the rest. But at least you got some computational parallelism in that search. All right, so hopefully now when you see our slogan, you go, yeah, it's not magic, it's Splunk. That's how they do it. It's not a magic box. It's just somewhat magic. All right, well, thank you for your time. I appreciate you guys coming.